Hello everyone. Today we're going to learn about recursion. Recursion may be one of the most difficult things to understand in software engineering, but it's really not. Recursion simply just a for or while loop with some overhead. Today we're going to learn why recursion is simply just a loop, how to use it, and what the overhead is. Prerequisite. Understanding function called stack and what it does to recursion is important. So make sure you learn this tutorial before continuing the current one. This tutorial is a part of the data structures and algorithms class. First, to set a theme for today's recursion tutorials, we want to remember that recursion is simply just a for or while loop. We're gonna see why in the details later. Recursion is probably one of the most scary things for most software engineers, but not after today. In general, recursion is simply applying the same function, the function that processes the data, with different data. So we think of recursion as a for or while loop, and we use recursion as a for or while loop. After today's tutorial, you're gonna be able to do so. Now, the most confusing thing in recursion is probably this line. This is a recursion function to calculate the factorial of a given number n. And in this calculation, we have a recursive call of factorial n minus 1. Whenever we see a recursion in a calculation like this, remember to go immediately to the bottom case and think up. And this is called bottom up. This calculation always waits for the base case. This is the base case, the exit condition. So if we run this code and draw out the call stack, we can see that factorial 3 is put on the stack, and also factorial 2 is put on the stack, and factorial 1 is the base case and it's on top of the stack. And everything down here of the call stack are waiting for the base case, factorial 1, to return a value. After factorial 1 return 1, factorial 2 is gonna be calculated, and then factorial 3 is gonna be calculated, and then finally the result is 6. This is a very simple example, but it explains very well what happens when you have a recursive call in a calculation like this. All of the recursive calls stack up and wait for the base case. Because it's so simple, I want you to vividly remember this photo. So whenever you see a calculation like this, you will never get confused. Again, whenever you see a recursion in a calculation, all the cases will stack up and wait for the base case output, like this call stack. Next, we're gonna see how recursion is a for or while loop with some overhead. So again, the recursion function itself is where we process one data point. And calling the function again with different data, which is our recursive call, is to process the next data point. This table is gonna list out the similarities and differences between recursion and loops with practical examples. First, with our 3 examples, we're gonna have a recursion version of the solution, and we're gonna have the loop version of the solution. And you will see everything recursion can do, loop can do it, and vice versa. Next, we're gonna have a look at example 1. Find the biggest integer in the array. We are already familiar with this solution from the previous for loop tutorial. So what we do is we loop through the array with the for loop. If we find an element bigger than the current max, we're gonna update the current max. And then when we finish the for loop, we return the current max. And if we run it, it's gonna give us 9. And the time complexity of this algorithm with for loop is O(n). And down here we have an equivalent recursion solution for the same problem. So what we do is we define an object to save the current max, and then we write our recursion function. It's gonna take in the array, the index, and the current max object. I'm gonna purposely print out the index and the element of that array at that index. First, we define the exit condition, also known as the base case, and then we apply the same logic that we have with the for loop. That if we find something bigger than our current max, we're gonna update our current max. And at the end, we call the recursive call and passing in the new data, which is the new index. And if we run this, it's gonna give us the same result with the for loop solution, which is 9. So this is how we use recursion to loop through array, and it also can be used to loop through string, matrix, and graph. Compared to our for loop solution, for loop move on to the next data point by the index and the syntax of the loop. Meanwhile, recursion move on to the next data point by calling the recursive call with new data, which is this set of data we have here. To exit the for loop has the condition function of the index. If the index equal to the array length, the loop will stop. Meanwhile, with recursion, to exit the recursion function, we have base case. So practically, base cases in recursion equal to exit condition of for loop. Now in this example number 1, we are processing the data while looping. We loop and we process the data. Same thing with our recursion here. We loop and then we process the data. You will see in the example number 3 that we're gonna process the data at the end later. Now let's talk about the differences between the loop and the recursion. That the for loop doesn't open any nested scope function, but the recursion does. You can see another functions get called within the function. So this recursion call gonna be limited by the maximum number of the code stack size. And because of this, recursion uses more RAM and CPU and less efficient than the for loop. But as we can see, both solutions have the almost exactly the same exit condition and processing logic. So basically, if you are given something like this in for loop, you'll be able to write the recursion version of it and vice versa. Meaning if you are given this recursion, you're gonna be able to use for loop to produce the same result like we have here. Next, we're gonna have a look at example 2. We're gonna see how to use both recursion and loop to loop through data points in graph. In this case, a binary tree. To quickly review this code, this is a structure of a node in a binary tree. We have the node data and we have the left and right pointer to point to the next node. And this is our tree. And when we create our tree with some data of the node, if we print it out, we're gonna have our tree look like this. This part should be familiar to you because it's from the tree data structure tutorial. And then we traverse the tree with while loop and a queue, meaning we're doing a breadth first search. So we start the queue with the root node, and while the queue has something in it, we get the node out and check if the node have a left or a right node, and we push those into the queue, and then we process the current node. In this case, we just save the data, and then we print out a result. And it's gonna print out 6, the first layer, and then the queue continue. Then we're gonna have 4 and 8, the second layer, and then 1, 5, 10. So this is a while loop solution to loop through graph. Now we're gonna have an equivalent recursion solution to loop through graph, and it's right down here. We initialize the queue, we initialize the result array, and we start the loop count. Then we define our recursion function, and on the top we always have our exit condition, which is if the length of the queue is 0. And you can see this is the same condition that we have for a while loop solution. Then we're gonna dequeue the data, see if the node have left and right nodes, and push it to the queue, and then print out the result. At the end, we keep processing the new data by calling the recursion function. And you can see that most of the logic here we have is almost exactly the same with the while loop solution. And if we run our recursion function, it's gonna give us the same result that we have here, 6, 4, 8, 1, 5, 10 with our while loop solution. Now for comparison, both recursion and loop can loop through graph data structure. To move on to the next data point, recursion use a recursive call and pass in the new data, while the loop just use its syntax. To exit the loop, the while loop have the condition in the syntax, and the recursion solution has the base case. So the base case in the recursion solution is equal to the exit condition in the loop solution. In this example, we are still processing data along the way with both solutions. We process data while we looping, and you're gonna see how we process data from the end bottom up in example number 3. And again, the recursion solution make a lot of function call within another function, so it's open a lot of nested scope function, and this is the overhead. It will depend on the max number of code stack size, and it's not gonna be as RAM and CPU efficient as the loop. Next, we're gonna have a look at example number 3 and see how both recursion and loop process data from bottom up. This is probably the biggest difference. So our problem is calculate the Fibonacci number of a position n. You should be very familiar with this problem by now, and we're gonna have a look at the for loop solution first. So to calculate Fibonacci n with for loop, we have f0 equal to 0 and f1 equal to 1. If n is either 0 or 1, we just return f0 and f1. If n bigger than or equal to 2, we're gonna have our loop, and we're gonna loop until n. We're gonna calculate fn and then constantly reassign fn minus 1 and fn minus 2 until we hit n. Then we're just gonna return fn. n. And if we run Fibonacci 10, that's gonna give us 55. And the time complexity of this solution with for loop is on. Next, we're gonna have a look at the recursion version of the solution. We have the base cases here, which is how we exit the loop. And then we're gonna have our calculation of fn. This is f minus 1 plus f minus 2. This is where we process the data from the n, bottom up. Whenever we see this, we immediately draw out the recursion tree, maybe just for a few layers, and then go straight down from the bottom and think up, because that's where the calculation actually starts. And that is exactly how we think of a solution, a possible solution. If we need data from the bottom up, we can either use recursion or the for loop version. But we always remember that this recursion opens a lot of nested scoped function, and because there are two of them here, so the time complexity of this solution is 2 to the power of n. It's very much less efficient compared to for loop. To improve the efficiency of this solution, we can do some catching to bring the complexity down to O of n, but that's what we're gonna learn later. So to summarize, we can use recursion and loop to loop through data points like array, string, matrix, and graph. We saw it in example 1, 2, and 3. To move on to the next data point, with recursion, we call the function again and pass the new data with it. That's our recursive call. With loop, we use the syntax of the loop to move on to the next data point. And we can see this in example 1, 2, and 3. To exit the loop, with recursion, we have base cases. So base cases in recursion is the exit condition. In loops, we usually have index conditions to exit the loop. We can see how to exit the loop in example 1, 2, and 3. To process data while looping, recursion can do it. Loop can also do it. And we see that in example 1 and 2. To process data from the n, bottom up, recursion can do it. Loop also can do it. And we see it in example number 3. The overhead of recursion happen everywhere. So we can see it in all of the examples. So to summarize, any capability to process data that recursion has, loop also has it. And that's why we say every recursion solution has a loop solution and vice versa, which means any loop solution has a recursion solution. But you always need to remember, recursion is not as efficient, and the max data size is usually limited by the code stack size. Next, how do we use recursion in our algorithm? Well, we can use it bottom up or along the way. These are the two ways that we can use to process the data. And more importantly, we just think of recursion as a loop. That's it, nothing more. If our solution depends on the bottom up values, which are the base cases, the recursion can help to make the code shorter, but remember the complexity will most likely gonna be higher. So we need to do some proper catching here to reduce the time complexity, which we're gonna learn later. Recursion adds some flexibility to continue the loop just by directly passing the new data to the call. For graph data, it does not need an index, which is why when dealing with graph data, we might see a lot of recursion. But this is also not encouraged because loop is almost always more optimized than recursion. And we have this photo here, the code stack, and the recursion tree of the factorial solution here, just again to remind that if we do bottom-up solution, it's always stacked up to wait for the base case output. That's the biggest difference of recursion solving problems bottom-up. There's an important note here that understanding recursion and how to use it is key to understand the algorithms that we're gonna learn later. So just to make sure to understand the similarities and differences between recursion and loop like we have in the table above, and make sure that you can use them interchangeably at ease, like whatever way you want. It's simple to understand, but you gotta do a lot of practice and reduce the example many times to have the concept in your mind. That is all for today's tutorial. Thank you for watching, and I will see you in the next video.